2 videos ago, we asked ourselves if we could find the basis for the column space of A. And I showed you a method of how to do it. You literally put A in reduced row echelon form. So this matrix R is just the reduced row echelon form of A. And you look at its pivot columns. So this is a pivot column. It has a 1 and all zeros. This is a pivot column, 1 and all zeros. And the 1 is the leading non-zero term in its row. And this is a pivot column. Let me circle them. These guys are pivot columns, and this guy's a pivot column right there. And you look at those in the reduced row echelon form of the matrix, and the corresponding columns in the original matrix will be your basis. So this guy, so the first, second, and fourth. So the first, second, and fourth columns. These, so if we call this is A1, this is A2, and let's call this A4. This would be A3, and this would be A5. So we could say that A1, A2, and A4 are a basis for the column span of A. And I didn't show you why 2 videos ago. I just said this is how you do it. You have to take it as a bit of an article of faith. Now, in order for these to be a basis, 2 things have to be true. They have to be linearly independent. And I showed you in the very last video, after the second in our kind of series dealing with this vector, I showed you that by the fact that, let's say that this guy is R1, this guy is R2, and this guy is R4, it's clear that these guys are linearly independent. They each have a 1 in a unique entry, and the rest of their entries are 0. So because all of the other, and this is true, we're looking at 3 pivot columns right now, but it's true of if we had n pivot columns, that each pivot column would have a 1 in a unique place, and all of the other pivot columns would have 0 in that entry. So there's no way that the other pivot columns, with any linear combination of the other ones, could never add up to each of them. So these are definitely linearly independent. And I showed in the last video that if we know that these are linearly independent, we do know that they are, given that R has the same null space as A, we know that these guys have to be linearly independent. I did that in the very last video. Now the next requirement for a basis, we checked this one off, is to show that A1, A2, and AN, that A1, A2, and AN, that their span equals the column space of A. Now, the column space of A is the span of all 5 of these vectors. So I have to throw A3 in there and A5. So to show that just these 3 vectors by themselves span our column space, we just have to show that, look, I can represent A3 and A5 as linear combinations of A1, A2, and A4. If I can do that, then I can say, well, then these guys are redundant. These guys are redundant. Then the span of A1, A2, A3, A4, and A5 doesn't need the A3 and the A5 terms. That we can just reduce it to this, because these guys can be represented as linear combinations of the other 3. These guys are redundant. And if we can get rid of them, then we'll show, if we can show that these guys can be represented as linear combinations of the other, then we can get rid of them. And then the span of these 3 guys would be the same as the span of these 5 guys, which is, of course, the definition of the column space of A. So let's see if we can do that. So let's go back to our original. Let me fill in. So each of these column vectors are A1 through A5. And then each of these column vectors, let me label them R1, R2, R3, R4, and R5. Now let's explore the null spaces again. Or not even the null spaces. Let's just explore the equations. AX is equal to, and let me write it this way. Instead of x, let me write x1, x2, x3, x4, x5 is equal to 0, right? This is how we define the solution set of this. All of the potential x1s through x5s, or all of the potential vectors x right here, that represents our null space. And then also let's explore all of the r times x1, x2, x3, x4, x5s is equal to 0. This is the 0 vector, in which case it would have 4 entries in this particular case. It would be a member of Rm. So these equations can be rewritten. I can rewrite this as, what were the column vectors of A? They were A1, A2 through A5. So I can rewrite this as x1 times A1 plus x2 times A2 plus x3 times A3 plus x4 times A4 plus x5 times A5 times A5 is equal to 0. Right? We've learned that was from our definition of matrix vector multiplication. And I just rewrote, this is just a bunch of column vectors A1 through A5. I drew it up here, A1 through A5. And I can just rewrite this equation like this. Similarly, I can rewrite this equation as the vector r1 times x1, or x1 times r1, plus x2 times r2, plus x3 times r3, plus x4 times r4, plus x5 times r5 is equal to 0. Now, we know that when we put this into reduced row echelon form, the x variables that are associated with the pivot columns are, so what are the x variables associated with the pivot columns? Well, the pivot columns are r1, r2, and r4. So it's r1, r2, and r4. That the x variables associated with them, we could call them pivot variables. And then the ones that are not associated with our pivot columns are free variables. So the free variables in this case, so x3 and x5 are free variables. Free variables. And that applies to A. This solution set, all of the vectors x that satisfy this equation also satisfy this equation, and vice versa. They're the exact same null space, the exact same solution set. So we can also call this x3 and this x5 as free variables. Now, what does that mean? We've done multiple examples of this. The free variables, you can set them to anything you want. So x3, in this case, x3 and x5, you can set it to any real number. You can set to anything you want. Set to anything. And then from this reduced row echelon form, we express the other pivot variables as functions of these guys. Maybe x1 is equal to, ax3 plus bx5. Maybe x2 is equal to cx3 plus dx5. And maybe x4 is equal to ex3 plus fx5. That comes directly out of the literally multiplying this guy times this equals 0. You would get a system of equations that you could solve for your pivot variables in terms of your free variables. Now, given this, I want to show you that you can always construct one of your, in your original vector, in your original matrix. So if we go to our original matrix, you can always construct one of the vectors that are associated with, we could call them with the free columns. You could always construct one of the free vectors using the linear combination of the ones that were associated with the pivot columns before. And how do I do that? Well, let's say that I want to find some linear combination that gets me to this free column, that gets me to A3. So how could I do that? Let me rearrange this equation up here. So what do I get? If I subtract x2, a3 from both sides of this top equation, I get minus, that's x3, a3. If I subtract x3, a3 from both sides of the equation, I get minus x3, a3 is equal to x1, a1 plus x2, a2 plus, I don't have the 3 there, plus x4, a4 plus x5, sorry, x isn't a vector, x5, a5. All I did is this I guess salmon-colored statement here is just another rewriting of this equation right here. And all I did is I subtracted this term right here, x3, a3, from both sides of the equation. Now, x3 is a free variable. We can set it to anything we want, and so is x5. So let's set x3 is equal to minus 1. So if we set x3 is equal to minus 1, then this term right here becomes a 1, right? Because that was minus x3. And let's set x5 equal to 0, as x5 is equal to 0. So if x5 is equal to 0, this term disappears. And I did that because x5 was a free variable. I can set them to anything I want. Now, I've written a3 as a linear combination of, I guess you could call it my potential basis vectors right now, or the vectors that were associated as a1, a2, and a4. a1, a2, and a4. They're the vectors in the original matrix that were associated with the pivot columns. Now, in order to show that I can always do this, we have to show that for this combination, there's always some x1, x2, and x4 that satisfy this. Well, of course, there's always some x1, x2 that satisfy this. We just have to substitute our free variables, x3 is equal to minus 3 and x5 is equal to 0, into these equations that we get from our system when we did it with the reduced row echelon form. So you get, I don't know if I even have to go through. In this case, you get x1 is equal to minus a plus 0, x2 is equal to minus c, so on and so forth. So you can always do that. You can always express the vectors. You can always express the vectors that are associated with the non-pivot columns as linear combinations of the vectors that are associated with the pivot columns. What I just did for a3, you could just as easily have done for a5 by subtracting this term from both sides of the equation, setting x5 to negative 1 and setting x3 to 0 so that the 3 term disappears, and you could run the same exact argument. So given that, I've hopefully shown you, or at least helped you see, or made you comfortable with the idea that the vectors, let me do them in a nice vibrant color, these magenta color vectors here that are associated with the free columns, or with the free variables, right? The free variables were x3 and x5, x3 and x5, and those were these columns right here, that they can always be expressed as linear combinations of the other columns, because you just have to manipulate this equation, set the coefficient for whatever you're trying to find a linear combination for equal to minus 1, and set all the other free variables equal to 0 that you're not solving for, and then you can get a linear combination of the vectors that are associated with the pivot columns. So given that, we've shown you that, look, these free vectors, and I'm using my terminology very loosely, but these ones that are associated with the non-pivot columns, can be expressed as linear combinations of these guys. So they're unnecessary. The span of this is equivalent to the span of this. The span of this is the column space of A. So the span of this is the column space of A. So in the last video, I showed you that these guys are linearly independent. And now I've showed you that the span of these guys is the column space of A. So now you should be satisfied that these vectors that are associated, let me do it in a blue color, that column vector, this column vector, and this column vector that are associated with the pivot columns in the reduced row echelon form of the matrix do indeed represent a basis for the column space of A. Anyway, hopefully you didn't find that too convoluted.